So as you can see, we have the random walk trajectories, and we say they are no longer distributed according to Pn, but we rather favor or penalize trajectories with a lot of touchings through this constant, which will be a real number. Now, the purpose is to study more closely this model, which has been also already discussed by Frank. This is the Hamiltonian. And let us recall what is this constant, the partition function. Okay, I actually prefer to indicate the dependence on the parameter in this way. I recall this is just, we have to normalize, so we have this sum times the probability of the trajectory, and just rewriting this by definition is nothing but the expectation under the random walk of the number of times the random walk hits 0 until time n. So this is our constant. And as it has been already done in the first tutorial by Nicolas, it turns out to be much more convenient to focus on the constrained partition function. Namely, we restrict the partition function to those trajectories that come back at 0 at the last time. So we rather define z and c, or 0. Okay, I will use the letter c, which is just the same thing. So exactly the same thing, except that we add an indicator function which kills every trajectory which does not come back to 0. Sorry, this is small n. Now, it has already been shown that this is a minor modification for what concerns our basic object, namely the free energy. So we will focus on that, and I recall you that the free energy, f of zeta, is the limit, as n goes to infinity, of 1 over n, the logarithm of the partition function, and I can add the constrained one without changing. So the free energy will be this function given by this limit. Now, if you're not very familiar with the statistical mechanics model, you may wonder why, after all, we are so interested in such objects, since we have been studying this over and over. Actually, the answer has been already provided partially by Frank in its first lecture, where he showed that if you know this function, actually you know a lot of information about the model. For instance, it's a very simple exercise to show that, well, first of all, this has already been shown, this is a convex function. So a convex function is quite regular, it's continuous, essentially is differentiable everywhere, but at most a countable number of points. And if it is differentiable at some point, then its first derivative is easy to verify, is just the limit of the derivatives of this function. And if you just compute the derivative, you get the expectation under our model of what? Of 1 over n, sum from I equal 1 to n, indicator function, wi equals 0. So what this formula tells us is that the value of this derivative tells us for n large, on the average, how many times will our model, our trajectory, typically cross the interface. So you see this is a number of times we cross divided by n, so the density of contacts. So this is a very important information. Actually, much more can be said. I don't think I will have time to go into detail, but one can prove that not only the average of this quantity converges to this constant, but there is a concentration. You can prove quite easily by very general result that the probability that this random variable deviates from its limit decays exponentially fast. So we really have quite strong result. But if I will have time, I will just mention. So hoping that now we are slightly more reassured and you are convinced that it may be interesting to study this object, we are going to focus on it. So We have seen a formula, an explicit formula this morning, and we are going to review the derivation to understand more deeply what's happening. But before that, I need some introduction, some preparation. In particular, I didn't tell you yet what are the assumptions we make on our random walks. So now I state them, and I will make also some very brief introduction on renewal processes that maybe not all of you know in detail. So there will be an introduction, and then the plan is an introduction, and then we will prove the formula for the free energy, which has already been proved by Frank, but we will look more closely at the proof, and then we will study the regularity. So first of all, assumptions on our random walk. Well, it should be rather clear that what really matters is the points at which the random walk comes back to 0. Because essentially we are perturbing our random walk by this kind of quantities. So it turns out to be convenient to let τ1, τ2, τ3, τ4 denote the epochs at which the random walk comes back to 0. So τ1 is the first instant at which Sn equal to 0, and actually τ0 equals 0, and more generally, τk plus 1 is just the first instant after τk at which Sn equals 0. Our assumption will be these two. First of all, that the random walk is recurrent. That is, τ1 is finite almost surely. And the second and most important one is that the law of τ1 has an asymptotical polynomial behavior. R of n, which is the probability that the first return to 0 takes place at n, behaves asymptotically as a constant divided by n to some power that we write as 1 plus alpha. So I'm talking of this sharp asymptotic behavior where C is a positive constant, otherwise this relation is just empty. And alpha is a real number, which we take between 0 and infinity. And, OK, we exclude 1. We exclude 1 just to avoid logarithmic corrections, but we could just deal with that. Frank actually mentioned you can treat a much wider class of models. You can allow logarithmic corrections here, but I will not do just for technical reasons. It's not really conceptually more difficult, but it's practical to focus on this class of models. Now, and of course, this is just the sum of R of n. Now, these hypotheses, these assumptions are very natural. For instance, you should know that if you take S a simple random walk on Z, namely Sn minus Sn minus 1 equals plus 1 with probability P, minus 1 with probability P, and 0 with probability 1 minus 2P, just a symmetric simple random walk where P is between 0 and 1/2, then these assumptions hold with alpha equal 1/2. Alpha will be a central object. I recall, I stress, is the exponent. Here I am excluding 1/2, which is the simple random walk case, just for a periodicity reason. If you take 1/2, then of course you can come back only at even sides. So as it is stated, this is not true because it's 0 for n odd. But it's just a minor point. You could just deal with that, but it's technically convenient to take this. Actually, much more is true because, in a sense, this assumption, the recurrency, could be dropped. Could be dropped. We could just not impose it. It's a minor modification. I will not do it, but you could really drop it. And now, this is the first generalization that one could consider. The second generalization, it will be clear, is that it's not necessary really to deal with the random walk on C. You can basically add any other process on on any space where there is a point that we call 0, and we are just looking at the returns to 0. You have to ask that these returns behave in this way. So in general, what I just want to say is that you could consider a Markov chain. Markov chain where there is a state where we call 0, and if you assume that the returns of this Markov chain have this asymptotic behavior, then you can study the model. I'm not saying this just for the sake of generality, but to stress that there are very interesting models. For instance, random walks in higher dimension. If you take a random walk in 2 dimensions, then, okay, the first return to 0 corresponds to alpha equals 0 here, but you have to add the logarithmic correction. But you can deal with that. Then if you go to dimension 3 and 4, etc., then you get, again, a polynomial behavior, but you have the probability is less than 1. What I want to say is that this can be treated in our model. I would just not consider for simplicity, but it's much more general than you could imagine. So these are the assumptions, and we will stick to that. And before going to the proof of the formula, let's recall what a renewal process is. It's just a notation for a very basic and important object. We have a random walk, and we have introduced the times at which the random walk comes back to 0. Now, what are the properties of such a sequence? Well, it's very easy to see that by the strong Markov properties, once you are back to 0, you start afresh, like at the beginning. So it's intuitively clear and easy to prove that the increments between T2 and T1 is independent of T1, and it has the same law. And this you can generalize. So by the strong Markov property of S, implies that the sequence tau k minus 1 is IID. So these variables are independent and have the same law. Okay? Yeah? 1, just for later convenience, because later you will see. Actually, we will, because in the result I will state there will be a logarithm. I don't want to bother. It has to be treated separately. But you could do it. Just make the computations. So these are IID. But this means that tau is itself a random walk. Is a process with independent increments. Positive increments, so not very random. It always goes in the same direction, but still. So tau, the sequence tau k, is a random walk with non-negative increments. And this is what is exactly the definition of a renewal process. So what is a renewal process? Just a random walk with non-negative increments. Actually, this is the last generalization I will mention. One could study our model just starting from a renewal process. You really don't have to bother about what is outside, but this is just a minor remark. Now, what does it mean more precisely? Let us be quite more precise. So if we fix, very simple observation, if we fix T1, T0, T1, and Tk, natural numbers, then the probability that T1 equal T1, Tk equal Tk, okay, is just the product for I equal 1 to k of R of Ti minus Ti minus 1. I recall you, R is just the law of the first return. This is just because, okay, this you can express by saying that tau I minus tau I minus 1 equal ti minus ti minus 1 for all I from 1 to n. And these are independent random variables. So you just get this formula. OK? Quite easy. And now a less easy, just a slightly more difficult question, but it will turn out to be important in a moment. Now I ask you, fix an integer n, and what is the probability that our renewal process visits n? Okay, you should imagine a renewal process is just a random walk with positive increments. It will do like this, and I want the probability that it comes back at n. It passes through n. So it could just follow this, but it could also make this, okay, or whatever. Okay? So the probability that, say, tau visits n is the probability, more precisely, that there exists an index k such that tau k equals n. Okay? Probability of the union over k, this means, of these events, tau k equal n. And now note that these events are disjoint, because if tau k equals n, tau k plus 1 will be greater, so it cannot be n. So this is just the sum from k in n of the probability that tau k equals n. And now I will go further. I would like to express more precisely this probability in terms of the law of the first return. How can I do? It's quite easy, just a bit messy, but first note that actually this sum I can stop at n, because, well, since each time I just make one jump, I cannot be at n after n steps. So the sum is from 1 to n, and, well, let us sum over all the position of the jumps before n. So I make a sum over 0, which is t0 less than t1 less than tk, which must be equal to n. These are the location where I have fixed. And then, recalling this formula, product for I equal 1 to n of R of ti minus ti minus 1. Okay? This is just the probability that tau k equals n. I just sum over the possible location of tau 1, tau 2, tau 3, tau k minus 1. And this, as we have just seen, is the probability that tau 1 equals t1, tau k equals tk. So, just a bit complicated, but I just stop here, and it will turn very useful in a moment. Now, what I ask you is, and this is the last thing we are going to say about renewal processes, is what is the behavior of this sequence? This is a real sequence as n goes to infinity. What do you expect? As n goes to infinity, what is the probability that your renewal process passes through n? Well, the result is known as renewal theorem. Is a quite simple result. Nevertheless, it has been proven for the first time in the 40s by Erdős, Pollard, and Feller. And it says that with no other assumption, is just that this sequence converges to 1 over the expectation of tau 1, where expectation of tau 1 is just, okay, sum for n equal 1 to infinity, n R of n. And this, of course, is at least a 1, because we are making steps of at least size 1. And it could also be infinite. Yeah? Yeah, you're right. You're right. A periodicity. I have to, you're right. The only assumption beyond this result, below under this result is that the law is not supported on a proper subgroup of n. Of course, if your steps are just even, you'll never come back at odd sides. But then you can restrict to even sides. So essentially, a periodicity. Okay, let's not mistake this. Now, this is an important result, but it's also quite intuitive when you think of it. Because, well, for large n, roughly the renewal points, the points in the renewal will be spaced roughly their mean. So if you fix a point, the the probability will be exactly on one of these is just 1 over the distance, the mean distance between the renewal. I don't know if I've been convincing, but try to think about that. It's not trivial. It needs a proof, but we will just assume it. So this completes the excursion on renewal processes. And now let us come back. Now it's really a moment to prove the formula for the free energy that has been anticipated and also described by Frank this morning. So back. Okay, no, before just one thing. If the expected value of T1 is infinity, then this is 0. Okay? And this is a poor result in a sense. You would like to know something more. This has been studied, it's been an object of deep research, but I will not enter into details. Now, let us come back. Recall. So, Z and C of zeta is expected value of E to the zeta, sum for I equal 1 to n, indicator of Wi equals 0. And we have, sorry, Si equals 0, and then Sn equals 0. And we want to study the asymptotic behavior of this. Now, first of all, for zeta negative, everything is very simple. Just told by Frank, if zeta is negative, then from this you see, well, this is the exponential of something negative is less than 1. So you just conclude that Zn critical is less than 1, okay? But it's also greater than, you just restrict to the probability of, to the event where you don't touch in any point except the last one. So you just have one touch, and you just take the probability of coming back just for the first time at the end. Now, this, by our assumption, look, is a polynomially decaying function. So we have that Zn is less than E zeta constant by n 1 plus alpha, and in less than 1. So once you take 1 over n logarithm, you get 0. Okay? So 1 over n logarithm of Z and C of zeta tends to 0 because it's switched by two sequences that goes to 0. Now, I'd like to stress how rough is this proof. We are just bound Z by two sequences which don't have the same behavior. This is constant, this tends to 0. Nevertheless, since we are looking for what is called the Laplace asymptotic behavior, that is, we are looking for the exponential asymptotic, we don't care about polynomials. Any polynomial bound here and here would be the same. Just means that 1 over n log tends to 0. This does not increase exponentially, does not decrease exponentially. The free energy is 0. So in a sense, the free energy is a very rough quantity. Nevertheless, it's very important, and it tells you a lot of information. So now just to recall you that for Z negative, everything is OK, and free energy it is 0, because the limit of this is 0. So now let us come to the much more interesting case of zeta positive. Now, how can we compute the free energy? Now we have all the ingredients. First, start from this and try to write more explicitly this expectation. You see, we have the exponential of these random variables. This random variable is the number of returns. Let us call Ln, is the number of returns of the random walks. So just sum over the possible value. Z and C of zeta is the sum for k equal 1 to n. K is the number, is the value of Ln. So on the event Ln equal k, we have E zeta k, and then we have the probability that Ln equals k, and Sn equals 0. Okay? Just definition of expected value. Now, what does it mean that Ln equals k and Sn equals 0? It means there are k returns, and at the end, the work is at 0. But this is just the same as saying that tau k equals 0. It's just the same thing. Tau k is the kth return. Saying that there are k return and that there is a return at n means that tau k equals n. And for this, we have the very nice expression that you liked, which is this expression. So let me write it. Sum for k equal 1 to n, E zeta k, and then we have to sum over tau 1, tau k minus 1, tau k, take a product, and we have this factor. Now, the first thing I'm going to do is to bring this factor inside. You see there is E zeta k, there is a product over, k terms. Then I just erase this, and I put E zeta here. Now, I'm quite happy with this formula. You maybe not, but why is this not so ugly? Because it resembles very closely this formula, you see? The probability that a renewal visits n is this double sum, this product of this kernel. So formally, we have the same expression here, except with a problem, an important problem, that the kernel is no longer R, and it is E zeta times R. Now, since zeta is positive, e to the zeta is greater than 1, and e to the zeta times R is not a probability, is more than a probability. However, the idea is just let us make this into a probability without destroying the formula. How will I do this? By this trick, I just multiply by minus R ti minus ti minus 1. I just add an exponential cutoff. Okay? And of course, if I want to do this, I have also to compensate. Now, what is nice is that these terms, since we have a product from 1 to n, and the tau I, this is a telescopic sum, all this term comes right out of the formula and gives E R n, because tau 1 minus tau 0 plus tau 2 minus tau 1 gives tau k, which is n. Yeah? Which one? This? This is ti minus ti minus 1. Okay, I try to write it bigger. Now, the point is, if I succeed in making this a probability, I'm done. Now, e to the zeta R of n, Okay, I come back here. It's also because it's quite, okay. So let me rewrite it. We have the sum for k equal 1 to n. Then we have the sum then we have the product for I equal 1 to k. And then we have E to the xi R of ti minus ti minus 1, E minus R ti minus ti minus 1. Hoping that you can read now. Is it okay? You have there in any case. And then here we have ERN. Now, what I'm just saying is that I'm hoping to tune R to make this a probability. This I can do. Why? This is quite simple, actually. Let me just erase. Because I want just that sum over n equal 1 to infinity of e to the c r of n e minus r n equals 1. Now, why is this possible? It's quite easy. Let us, for simplicity, introduce the generating function. We have seen a lot of generating function of the sequence Rn. Okay? Then we can re-express this condition by saying that phi of E minus R equals E minus zeta. And why it's always possible to do that? It's quite simple. Just because phi of 0 is 0. Phi of 1 is 1. Phi is increasing, continuous. It's analytic, actually. So there will be, since zeta is positive, this is a number which is strictly between 0 and 1. And it's always possible to find actually a unique R which satisfies this relation. So I fix R in this way. It's just a trick in a sense, but it's a very effective trick. Why? Because now this is what I will call R tilde zeta of ti minus ti minus 1, where R tilde zeta is just this. And then this is a probability. And all this very ugly and messy expression has a meaning, has a probabilistic meaning. Just come back here. We have told, I just told you that if you have a renewal process, the probability that this renewal visits n is this big sum where R is just the law of the increment. So here we have a different law. No problem. Let's consider a different renewal with this law for the increments. And then, so all this stuff we can write as P tilde zeta tau visits n, where what is P tilde c is just a law. Under this law, tau k is a renewal process with law P tilde zeta tau k plus 1 minus tau k equals n is just R tilde zeta of n. Okay? This is just a trick, but we are done. Because we have a remarkable probabilistic interpretation of the partition function. Is a pure exponential e to the times r times n times an explicit constant. Constant depends on n. But we know what is the asymptotic behavior. I just told you about the renewal process. I told you that if you have a renewal process, the probability that it visits n, for n that goes to infinity, tends to 1 over the mean. And look what the law looks like. Remember, R of n is our starting law, which has a polynomial tail. However, here we are adding an exponential cutoff. So R is strictly positive. So it's clear that this law has a finite mean. Okay? So, finally, this constant converges as n goes to infinity to 1 over E tilde zeta of tau 1. And this is strictly positive. This is a constant in 0 infinity. So finally, what we have proven is that for the value of r, which solves this equation, we have that the partition function is asymptotic to exponential of Rn times a constant. Well, this is much stronger than proving that the free energy is this constant, because now we take 1 over n logarithm, and of course 1 over n log gives r. This is a constant, disappears. So in particular, 1 over n logarithm of Znc of zeta, if you take the limit as n goes to infinity of this, which is just the free energy, this is exactly R, where R is the solution of this equation. So, first of all, we have proven the the explicit formula for the free energy. The free energy for any zeta is the unique solution of this equation, where phi is the generating function. And second, I'd like to stress this, we have obtained much more than just the free energy. As you have seen in Gordon's course, for self-avoiding walk, you conjecture that the asymptotic behavior of the total number is an exponential times a polynomial where the exponent is universal. However, it's difficult to prove that. Now, in this much more simple case, we can prove that this quantity is asymptotic and exponential times a constant, an explicit constant. So we have a precise control. And with this, you can prove a lot of much deeper things. I will not have time to go into detail, but at least we have obtained the formula for the free energy. OK. So this part is over. We have obtained the formula for the free energy. And now we are done. And we are ready to study it, to see what can be extracted from this formula. By the way, you may ask if this strange renewal process has a meaning, because it's just a trick in a sense, okay? We have just found this algebraic structure allows for this representation. Well, it's definitely not a trick. This renewal process describes essentially the distribution of the returns to 0 of our model for n large. So the simple random walk had returns which had a law which is Rn. This is the probability of the first return. Well, what I'm telling you is that for zeta positive and n large, under our polymer model, the returns are described by this new law. This I will not have time to prove, but it's not difficult to do it, and this is the key result, essentially. Now, regularity of the free energy. This is zeta, this is f of zeta, and I make a drawing. It is 0 for negative, and then becomes positive. It's also convex. Here I'm quite vague, this depends, and we will see in a moment, but this is roughly the graph. So the free energy, I recall you, is 0 if zeta is less than 0, and also equal to 0, and it is the only solution R to the equation phi of E minus, okay, the only solution to this equation. E minus theta if zeta is positive. Now, what do we want to study? I mean, the point is, from this explicit expression, which is valid when zeta is positive, you can extract a lot of information of f. The first information, which I will just describe very quickly, is that f restricted to positive value is an analytic function. Why is this? This is quite easy. Well, phi, where is phi? Here is phi. Phi is analytic. It's just a power series. Okay? Analytic function, and it is increasing from 0 to 1. So it's invertible. Its derivative never vanishes. So its inverse is also analytic. The inverse of an analytic function is analytic whenever it is defined. So if you just invert this relation, you see that essentially f of zeta is minus the logarithm of phi minus 1 of e minus zeta, which is not a nice expression, but shows that it is analytic. It's a composition of analytic function. So you have a function which is analytic here. Well, analytic here, it is 0. But then what you immediately discover, it is not analytic here. By the principle of identity of analytic functions, the function cannot be analytic in any neighborhood of 0. 0 is a non-analyticity point. Because if it were analytic, since it coincides with 0 on the left, it should be 0 everywhere. Okay? Two analytic functions that coincide on a set which has an accumulation point must be equal. So you see, it's a strange function because it's composed by two branches. Each of one is analytic, but you have the point in which they meet, and it's where they are not. It's not analytic. So it's nice to understand what's happening here. It's not analytic, but it is continuous at least. This follows because it's convex, just this, or for the explicit formula. But what is the regularity? Since it's not analytic, it may happen that its first derivative is discontinuous. Or maybe the first derivative is continuous, but the second derivative is discontinuous at 0. Or maybe the second is okay, and this is the third, which is discontinuous. Now, in general, when the kth derivative is the first derivative to be discontinuous, we say that there is a kth order phase transition. So a phase transition happens whenever at a certain point the free energy is not analytic, and the order of non-analytic of the phase transition is the degree of non-regularity. So what we are going to do quite easily now is to study the behavior of f here to understand what's the order. Now, how can we do? It's just a matter of understanding the behavior of phi in order to invert. Now, the first observation is, well, let us set r bar of n, the sum for k greater than n of r of k. This is the integrated tail, okay? And this, by our assumption, is a constant divided by alpha. It's just another constant, 1 over n to the alpha, 1 plus small o of 1. Because this is a constant divided by k, 1 plus alpha, 1 plus small o of 1. So you just sum and you get this, like an integral, easy exercise. Now, in order to study it, it's convenient to make an integration by parts, actually, a summation by parts. This is a good exercise, just a combinatoric exercise, quite easy, to see that 1 minus phi of x, it's just, you can write as 1 minus x psi of x, where psi is just the generating function of the r bar. Sum for n equals 0 to infinity of r bar of n, x to the n. While I recall you that phi of x is just sum for n equal 1 to infinity of r of n, x to the n. I mean, you take phi, you just write r of n, easy exercise, as r bar of n minus 1 minus r bar of n, okay? You write as the discrete derivative of its primitive, then you separate the sum, you change index, you put everything together, and you get this other formula in which you derivate this. And if you derivate this, you get xn minus xn minus 1, which gives you this. But this is just easy exercise. So take this for granted for the moment. And now, what's happening? Look, what is psi of 1? Psi of 1 is just the sum for n equals 0 to infinity of r bar of n. And r bar of n, I recall you, is the probability that tau 1 is greater than n. But then you should have met this formula once in your life. This is the expected value of tau 1. Okay? This formula holds for any positive random variable. And then if you remember that this is roughly 1 over n to the alpha, you see that there is a huge difference if alpha is less than 1 or if alpha is greater than 1, because then this sum converges or diverges. So this is finite if alpha is greater than 1, and infinite if alpha is, on the other hand, between 0 and 1. And also for alpha equal 1, but this you should handle separately. But now, if alpha is greater than 1, then we are done, because just let me remind you, now my aim is to study the behavior of f for small zeta. This means studying the behavior of phi for its argument that approaches 1. And thanks to this, I have a nice expression. So, first case, alpha greater than 1. If alpha is greater than 1, psi of 1 is a finite constant, but then from this, I abstract that 1 minus phi of x, okay, sorry, is equal to 1 minus x times a constant, c, which is 1 plus small o of 1. Okay? This is 1 minus x, as x goes to 1. But then we can easily see that 1 minus phi of E minus the free energy is equal to 1 minus E minus the free energy times a constant times 1 plus small o of 1. And then this, of course, this since as zeta goes to 0, now we are taking zeta going to 0. So the free energy goes to 0. So this is just f of zeta times a constant times 1 plus small o of 1. So if 1 minus this has this asymptotic behavior, then from this relation, 1 minus the free energy should be equal to 1 minus E minus zeta. And 1 minus E minus zeta is just zeta, 1 plus small o of 1. But then you just look at both sides and you obtain that the free energy is equal to zeta divided by a constant, 1 plus small o of 1, as zeta goes to 0. So if alpha is greater than 1, then we have a positive right derivative at the origin. We have a first order phase transition. It's a very regular function. Why is this nice? I mean, this is nice. Why is this interesting? Because as I told you, the derivative of f is the contact density, the positive, the fraction of points where the model touches the interface. So if we make f prime of zeta as a function of zeta, the graph it's 0 until here, and then it has a discontinuity. So you see, we call a phase transition because this is a phase transition because there is a very striking feature in the system. You just change your parameter a little bit, and something drastic happens. Below 0, you have zero contacts, and above 0, you have a positive contact. So this is what's happening. Finally, what happens for alpha between 0 and 1? This is a good exercise of Riemann sum approximation, because essentially we want to study the behavior of phi as x goes to 1. We have extracted this, and then we have this other function. This other function, before it was for alpha greater than 1, tends to a constant, and we are happy. Now, for alpha between 0 and 1, this other function tends to infinity. So we have to understand which is the rate at which tends to infinity. Now, recall that psi is this. Now, psi of E minus R equal the sum for n equals 0 to infinity of R bar of n E minus Rn. As r goes to infinity, diverges. So this means, first thing, that I can neglect any finite number of terms. Look, if I fix an n, this, as r goes to 0, gives a constant. So any finite number, any finite term is constant is the limit as r goes to 0. So I can forget it. And since I know that the whole sum diverges, I get something which is equivalent. So when I write this, I mean up to 1 plus of 1. So I can start the sum from any n0. But then, if I start from n0, I just replace this by its constant, its asymptotic behavior. Okay? I've been quick, but this first step is just to tell you that if you're just interested in the rate of asymptotic behavior, you can replace this by its asymptotic behavior, and then you can forget the first n0 term. And now I ask you, what is the behavior of this sum? As r goes to 0, because as you see, r goes to 0, this disappears, and you get the divergence sequence. Alpha is between 0 and 1. Now the trick is to make an integral appear. So what we are going to do is put r here, okay? And then we have to pay r to the alpha. And then what I'm going to write is just I bring out the constant c over alpha, and I want also another r appear. So I write r alpha minus 1, and then sum over n, well, n0 to infinity, r times e minus nr divided by nr to the alpha. Now, why did I do this? Because this is a Riemann sum. R is a small parameter, and then this I can write it as a sum over t, which belongs in Rn of r times e minus t divided by t to the alpha. So n times r, I call it t, so it's just a natural number multiplied by r. Okay, I have to start from Rn0, but this is irrelevant. And since what I'm just doing is I'm just making small interval of weight r, and I have this function, which is like this, and I make just a Riemann sum, the value of the function at the interval times the width of an interval. So this converges to the integral from 0 to infinity of e minus t divided t to the alpha dt. And this integral is finite. It's finite because close to 0 there is no problem, because alpha is between 0 and 1. And close to infinity there is no problem because we have the exponential. The fact that this actually converges is easy to verify because you have a monotonicity, so you can bound this sum from above and from below by the integral, just switching one step to the left and to the right. In any case, this is a constant. It's actually gamma, Euler gamma of 1 minus alpha, but just a positive constant. And then what we have obtained, look here, is that psi, the e minus r, is a constant times r alpha minus 1. And then we are done, finally, because we have 1 minus phi e minus free energy equals, I take this formula is 1 minus E minus free energy, okay, times psi of E minus the free energy, which is free energy alpha minus 1 times a constant. But then 1 minus E minus free energy is just free energy. Then we get F of zeta to the alpha, 1 plus small o of 1, and then you have a constant. So 1 minus phi E minus free energy, it just behaves like this. Recall the formula for the free energy. 1 minus phi of the free energy is also equal to 1 E minus zeta. That is zeta, 1 plus small o of 1. And then you look at this, and you get finally that f of zeta is equal to zeta to the 1 over alpha times a constant times small order terms. So as zeta goes to 0, the free energy goes to 0 with the power 1 over alpha. Since alpha is less than 1, this power is greater than 1, so we are more regular than linear. It has the derivative goes to 0, and the smaller alpha, the higher this exponent, and this gives you a regular behavior of the free energy. So it's as regular as you wish by taking alpha smaller. So this completes the study of the regularity of the free energy. Much more could be said about these models. In particular, as Frank mentioned, you could consider an interaction not only with one interface, but with several different interfaces. And some interesting feature emerges, but okay, we just don't have time to discuss it, so I just close here. So thanks. I don't know. System. Actually, this trick actually we have discovered after. It's actually quite common. I mean, if you have a super probability, something which is not probability, this trick of adding an exponential cutoff to make it a probability works in different contexts. Actually, we discovered by chance that it works here, but for instance, also in queuing theory, it's used. There is a beautiful book by Asmussen where it's studied in depth. So,
yes. Why? I mean, and here it works very simply, very beautifully, because you make the remark that this tilted R has a meaning.
Yeah.
It is the typical behavior of your polymer.
Yeah.
Once it is absorbed. So what you're doing is you're tilting it so that you get the behavior, so that the behavior of your polymer is now becoming typical under this new law.
okay.
So it's perfectly like that. But here it's so direct that you just see it in front of your nose. But that's a good question. It's exactly that.
Okay, thanks.